All right, so for this one, we're going to be going through part B of question 5. Sorry, I had to separate the videos into two. They were just getting too long. So for part 5, in question 5, part B, we're taking a look at case 1, 25 degrees C. Some important information to pull is we have our differential pressure, our differential stress. It's going to be 200 megapascals. So that's sigma 1 minus sigma 3. So sigma 1 minus sigma 3 is 200 megapascals. If we look at the minimum confining pressure from our question 1, right, it was 50 megapascals. So sigma 3 equals 50 megapascals. And because we know the differential stress and then we know the minimum stress, we just add the minimum stress to the differential stress, and that gives us our sigma 1 value. The other important piece of information that we're going to have from this is that we have our conjugate sets, which were found to be failing at 72 degrees. This is the angle of failure. So this is going to be the angle from our Morse circle that intersects that circle. So we'll construct this first and then go from there. So we've got our minimum stress at 50. So that's sigma 3. Sigma 1 is at 250. And our differential, our origin for this circle is going to be 150. We take our compass here and draw in eventually our circle. So there is our circle. And again, we know that the failure is 72 degrees. So in order for this to be on the right side of the circle, right, it has to intersect our failure envelope, which comes from this direction. So the 72 degrees actually is coming up from this angle, which ultimately makes the 2 theta is going to be 108 degrees, which is our 180 minus 72 is 108 degrees. So that is our 2 theta. From that, right, we want the tangential point here, right? So the tangential point is basically 90 degrees from the intersection of this circle. So you measure it up, right? We want it to be perpendicular to this, and we draw our tangential point here. So this is our 90 degrees. And a couple of things are happening. First off, we can find the cohesion, our S naught. This from the handout that I gave you guys over here. The cohesive strength, sigma naught, is the sigma S value on the failure envelope where sigma N equals 0, basically where the failure envelope crosses the y-axis. So here we can see it is about, we'll say 59 megapascals. If we want to find out the angle of internal cohesion, this part I'm going to give you guys the points back, because what you do is you take your 90 degree mark. Here the equation I gave you was 90 minus 2 theta. It should have been 2 theta minus 90, and that would have given you this guy, and that's how you could have figured out the coefficient of internal friction. But you did not have that. So here we're going to figure out the angle between this, which is 18 degrees. 18 degrees. And then our mu, which I also labeled wrong, is the tangent of our 18 degrees, and that is 0.325. And at the instant of failure, our sigma n, right, we're just going to read it from our graph. This is our instant of failure, is at 120 megapascals, and our sigma s is about 95 megapascals. So here we've determined mu, the internal friction, we've determined the cohesion amount, and our sigma n, sigma s at the instant of failure.